All right, everyone. So I'm going to be talking about Chapter 5, Section 5.1, which is the applications of Green's second theorem. So Green's second theorem is just this long equation up here. You don't need to look too deep into it, but it's really just relating some volume integral over some scalar functions times the Laplacian of those scalar functions to a surface integral of those same functions. And what we're going to be using this to do is find a solution to Poisson's equation. So for the general electrostatics case for a point charge, or not necessarily a point charge, but just electrostatics in general, we can say that the Laplacian, which is del squared of our potential, is going to be equal to negative 4 pi times some charge density. Okay? And then the other thing that we're going to notice is that there's these psi's here. Okay? And these psi's are just scalar functions. And so since this Green's second theorem is going to be true for any scalar function, we can replace these psi's with another scalar function. And so what we choose to do is we choose to replace it with something called the Green's function, which is going to be a function of r and r prime. And we define this such that the Laplacian of the Green's function is going to be equal to negative 4 pi times a delta function of r minus r prime. Okay, and so this r kind of came out of nowhere because there's no r in the Green's second theorem, but all we really have is some general case where we have some point charge, some origin, and then some point that we want to find the potential at. We define the vector from the origin to the charge as r prime. We define our vector from the origin to the point we want to look at as r, and then we can therefore define the vector from q to phi as just being r minus r prime. Okay, and so what we can now say is that our Green's function is defined, okay? And essentially what that allows us to do is say that we can redefine, or not redefine, but I guess plug in for the stuff in Green's second theorem, okay? So we're going to rewrite Green's second theorem. So we have some volume integral, we have our potential, and then we're multiplying that times the Laplacian of psi. But we said the psi is now actually the Green's function, right? So psi turns into the Green's function, and we said that the Laplacian of the Green's function is just equal to negative 4 pi times the delta function. So we have negative 4 pi times the delta function in place of the Laplacian of psi. And so we can then now subtract our Green's function. Remember, we're replacing psi here with, so we're replacing psi with the Green's function, and then we can multiply that times the Laplacian of phi. But we actually define the Laplacian of phi here because it's just Poisson's equation. So we replace that with negative 4 pi times rho, which is our charge density. And then we write this as, an integral over some volume. Okay, and this volume is like some arbitrary volume. So if we have some arbitrary volume with like, charges in it or whatever, or just like, let's say it's a uniform charge density, some rho, then, the surface integral is integrating over the surface, and then the volume is obviously integrating over the volume. And so we have a surface integral, dA prime, or that's our differential, or whatever you call it, and then we're dotting that with our scalar functions, and then we don't know what the gradient of g or the gradient of phi is, so we're just going to leave them how they are. Okay, so we're going to place psi with our Green's function, and then we're going to replace, or we can just leave phi actually, but we're going to write our gradient of phi. And then there we go, and then we have that. Okay, And so one thing we can do here is we can notice that we have this difference in our integral. And so, we can split this integral into two different integrals. So the first integral we can look at is this integral over the volume of our phi times our times some delta function, and then times negative 4 pi, and then we're integrating over some volume. And then you should understand what a delta function is if you're watching this video. So this is just going to simplify to phi of r. Sorry, not the integral of phi of r. This entire integral just simplifies to negative 4 pi phi of r. Okay? And this is what we're looking for in the end, right? We're trying to solve for phi of r because we want to be able to find our potential at any point in space based on the charge configuration. Okay? And so we are now able to get rid of that first part, that first integral, and replace it with just that negative 4 pi phi of r. So now we have negative 4 pi, and then I'm going to pull out the negative 4 pi also from this. So we have negative 4 pi times phi of r minus the integral over the volume. So we're going to integrate over our volume of our the part that starts with the Green's function. And then we pulled out the negative 4 pi already, so we can get rid of that. And then we just have a rho of r prime, and then we're integrating over tau prime or d tau prime. Right, and then we can't really simplify anything in this integral, so we're going to leave it as it is. So this can be equal to surface integral dA prime dotted with, actually I think I can just copy it down. All right, and so we have our surface integral, and we can now, since we want to just solve for phi of r, we can isolate it by first dividing by negative 4 pi, and then adding this to the other side, and then we find that phi of r is equal to negative 1 over 4 pi times the surface integral of dA prime dotted with phi of r prime times the gradient of the Green's function subtracting the Green's function times the gradient of phi, and this is going to be added with this volume integral here. And so we can add the volume integral of our Green's function times our charge density function, integrating over the volume, obviously. And then this is actually just a complete representation for the solution to Poisson's equation for some general potential under general boundary conditions, because we haven't defined the gradient, or which is really just the derivative, right, in multiple dimensions, I guess. At least that's how I like to think about it as a physicist. Maybe the mathematicians might be mad about that, I'm not sure. But what we can say is that we didn't define our gradient to be anything. So this is actually just for general boundary conditions. And we didn't define our potential to be anything. So this is just some general potential. We didn't define our charge distribution to be anything specific. So this is a general charge distribution. So this is like just the most general solution to Poisson's equation for some electrostatic charge, general electrostatic charge configuration, and with general boundary conditions. And so that was the entire point of this short little section. And so there we go. That's it.